will continue. By the way, before I forget, of course, I put it also on warm-up announcement. Tomorrow we will not have a Zoom session because I'm attending actually conference, but I will send you in the afternoon the password for taking the quiz. Okay.
Sounds good.
All right. So today we are going to talk about section 14.4, and if we have time, actually, we'll go to section 4.5. That is talking about gradient and directional derivative. Actually, this is a serious material that we need to know because gradient is a vector, and we are going to work with vector field. So we have to have a slight concept of what the gradient look like. But on that way, we will talk about directional derivative. So what is our objectives? Upon successful completion, you should be able to find the directional derivative of function of two variables, find the gradient of a function of two variables, and work with properties of gradient. These are our goal. As you might remember, actually, or know it, the partial derivative of functions of a function is equal to f of x at the point x sub 0, y sub 0 are defined as this is in the x direction, and this was a partial derivative with respect to y. That means the rate of change in the y direction. Now let's define directional derivative. What about in any direction? So the directional derivative of a function of two variables is defined like this. Suppose z equals f of xy is a function of two variables whose domain is D, and x sub 0, y sub 0 is an interior point of D. If it is an interior point of D, then we can really talk about directional derivative. So if u is a unit vector, which is defined by trigonometric function, because it can cover everything, cosine of theta I, sine of theta j, and theta is between 0 and 2 pi, is a unit vector. The directional derivative of f at the point x sub 0, y sub 0 in the direction of the unit vector is a number. Remember, it is a number because it is the rate of change. Direction of the function at the point x, y, x sub 0, y sub 0 in the direction of u is the limit of that function, x sub 0 plus h times cosine of theta. That means the x direction, y sub 0 plus h times sine of theta minus f of x sub 0, y sub 0 over h. This, provided this limit exists, then it's the limit definition of derivative. I'm not going to really spend a whole lot of time on using the. So we'll go directly to theorem 1. If z equals f of xy is a differentiable function, then the directional derivative of f at the point x sub 0, y sub 0, the direction of f is the unit vector u, which has a component u1, u sub 2, is given by the partial derivative with respect to x multiplied by the x component of the unit vector plus the partial derivative of y with respect to, the partial derivative of f at the point x sub 0, y sub 0 with respect to y multiplied by the unit vector y component. That unit vector is a trigonometric function. The x component will be cosine, the y component will be sine. Of course, you are aware of that. So why not we do this size? It has three components. A, find the directional derivative of f of xy in the direction of u of the function f of xy is equal to x squared y plus y squared in the direction of unit vector cosine of pi over 4 I plus sine of pi over 4 j. B, what is the directional derivative at a specific point? That means at the point 1, 2. C, I want to interpret this directional derivative as rate of change. Please do that. Here it is, and then we'll work on it. Okay, if you try it this much, let us do it together. So what is really the partial derivative of these two functions? That is our focus now. And if we get those partial derivatives, what are the partial derivatives of this function now? And if we get those partial derivatives, then we can really move forward. Moving forward, the partial derivative of with respect to x, this is constant, y is constant. So therefore, it will be 2xy. And the partial derivative with respect to y, this is 1. So x squared times 1 is x squared plus 2y. And as you see, this is polynomial and this is polynomial. Both partial derivatives are continuous. If the partial derivatives are continuous, then the function is differentiable. Remember, differentiability of functions of two variables. The two partial derivative has to be continuous in order the function to be differentiable. So we can use theorem 1 with the unit vector. This is radical of 2 over 2i plus radical of 2 over 2j, because sine of 45 degree is radical of 2 over 2. Then the partial derivative of f of xy is sine of theta. So here we have 2xy multiplied by cosine of pi over 4 plus x squared plus 2y multiplied by sine of pi over 4. Well, obviously, this one we call it a radical of 2 over 2. That means simply this is square root of 2xy plus square root of 2 over 2 is that, and this multiply this polynomial, and that is it. We're done. Then what is the partial derivative at a specific point? Then b. The partial derivative, I mean the directional derivative of f at the point 1, 2. That is what we are asked in part b. Well, it is going to be when x is 1 times 2 plus radical of 2 over 2 and 1 square plus 2 times 2. And this equals 2 times square root of 2 plus radical of 2 over 2 times 5. All right. So now what we have to do is really let us multiply by this. 2 times 2 is 4 because I have radical 4, 5, and that is 9. Well, we can really use your calculator and approximate. What is the calculator value? Anybody who has a calculator?
6.36.
Okay, 6.36. Do you have any other digit?
6.36396.
Okay, let us make it 4. That's it. Thank you. So this is it. So let me write it here. So see, what is our interpretation? Our interpretation is when we are at the point 1, 2, and moving in the direction of actually the unit vector, which is radical of 2 over 2 in the x direction and radical of 2 over 2 in the y direction. The function f is changing. at the rate of approximately 6.364 units per unit length. And that's it. So now I want you to do this. Example 2. Find the directional derivative of f of xy that is defined by x times sine of y at the point 2 pi over 3 in the direction of the vector v, which has 3 in the x direction and y in the 4 in the y direction. And I want you to interpret this result as the slope. So the first thing first, find the partial derivative. And if you, obviously, this is trigonometric and polynomial, the partial derivative is going to be continuous in all real number. So it is differentiable. Then find the vector and find the directional derivative. Go ahead. So when you differentiate this one with respect to x, sine of y is constant, so the derivative of x is 1, so you'll have simply sine of y. And the partial derivative with respect to y, x is a coefficient, and the derivative of sine is cosine. And that is what we have. Since both are continuous, that's what we need. And now, remember, directional derivative can be done with unit vector, not vector v. So we have to normalize it. That means what? The vector v, which has 3 and 4 as a component, divided by the square root of the magnitude is 3 squared plus 4 squared. That means 1 over square root of 25 is 5, and 3 and 4 we have, and that is actually 3/5 and 4/5 is our unit vector. Okay, if we get 3/5 and 1/5 as our unit vector, and now the next one is we need to come up with a directional derivative. The directional derivative of f of xy in the direction of u is going to be, well, the x component, which is 3 over 5, multiplied by sine of y, plus 4 over 5, multiplied by x times cosine of y. That is what we have to do. And this is really the directional derivative. Then at the point, at the point 3, 4, which is where, I'm sorry, 2 and pi over 3. Then what we need to do is the directional derivative is going to be 3 over 5 sine of pi over 3 plus 4 over 5 and x is 2 cosine of pi over 3, and this will give us 3 over 5 is the x component. I will leave that one, but sine of pi over 3 is radical of 3 over 2, and plus this is 8 over 5, and cosine of pi over 3 is 1/2. So when we see we have the least common denominator, we can make it 10, and you have 3 radical of 3 plus 8 over 10, and that is actually the approximate value for this one. If you multiply 3 times square root of 3 and add it on it and divide it by 10, I think you get approximately 1 point, check guys, 1.32, yes? Make sense, guys? Is it 1.32? Okay. And now, what is our interpretation? Well, the interpretation of this one is, look, we have this surface, and the directional derivative is you are going to have a plane which is perpendicular to the xy plane connected with this curve. And when that plane and this surface are connected, they are going to create a line at the point 2 pi over 3, and the z value is going to be 0. So that is the slope of the tangent line to the curve C formed by the intersection of the surface of f of xy sine of x times sine of y, and the plane perpendicular to the xy plane that contains the line through the point this and in the direction of v, and that is approximated by 1.32. That is what it means. Okay, from here, actually, the main focus of our lesson is going to be defining gradient. So how is gradient is defined? We can express the directional derivative of this with as a dot product of two vectors as follows. So the directional derivative of f as a point x sub 0, y sub 0 in the direction of u is f of the partial derivative with respect to x at the point x sub 0, y sub 0 times u1, and the partial derivative with respect to y at that same point multiplied by u2, u sub 2. That means u sub 1 and u sub 2 are the components of unit vector. If that is the case, actually we can really write this one as the following. Because this is a dot product, the partial derivative with respect to x, that is the I component, and that is the g component. And this is multiplied by the vector u sub 1 I the direction and u sub 2 the direction of g. And that's it. Well, let us write it in component form. So we write it like this. So this one we represented by a vector like this f, and that is dotted with the unit vector u. So this is the definition. Let z equals f of xy be differentiable function. The vector, this one, we read it as del f of x, y, is called the gradient of f and is defined as the gradient of f is the partial derivative of that function in the x direction plus I, the partial derivative of that function in the y direction j. So this is how we actually define gradient. So because we define it this way, we have the following theorems. Theorem 2. The dot product of the vector del f and the unit vector u is the scalar that is equal to the directional derivative of f in the direction of u. That is del f dotted with unit vector u equals directional derivative of f of xy in the direction of u. All right, then let's do example. I want to find the gradient of the function f that is defined by x cubed plus y at the point 2, 1. And I want to use the gradient to find the directional derivative of f at the point 2, 1 in the direction from actually point 2, 1 to 5. Go ahead, we'll do that. Okay, let us do this one quickly and then move on. So when you differentiate this one with respect to x, it will give you 3x squared and y is coefficient. And because this is the form of product is given, by the way, this is I, and plus, let us differentiate with respect to y, and x cubed is the coefficient, and that is g. So del is this one, and the gradient of f at the point 2, 1 is 3 times 2 squared times 1i plus 2 cubed j. So 2 square 12. That's it. So we answered A. Then B. The unit vector. First of all, we are really going from this direction to this one. So the unit vector u from the point 2, 1 to the point 3, 5 is, well, as you know, u is the direction vector divided by that magnitude. So the x component is going to be 3 minus 2. And the y component is 5 minus 1 over the square root of 3 minus 2 squared plus 5 minus 1 squared. Is it clear what I'm doing, guys? Because when we use directional derivative, we have to make sure that it is a unit vector. And this is 1, and this is 4. And this one is square root of 17, because 4 squared is 16, 1 squared is 1. Okay. We have that. Then what is the directional derivative? At the point 2, 1 is the gradient of f at the point 2, 1 dotted with the unit vector. And that is going to be 12, 8 is going to be dotted with 1 over square root of 17, 4 over square root of 17. Okay, so this is going to be 12 over square root of 17 plus 32 over square root of 17. That's going to be 44 over 17 times square root of 17. And that's it. So the directional derivative in the direction of u is 44 square root of 17. And that's it. Oh, by the way, if you don't see what I am writing, please tell me to push it back. Everybody gets this?
Yes.
Okay, shall we move on?
I have a quick question. Does the gradient, can we talk about gradients and directional derivatives for functions of more than 2 variables, or does this definition only apply?
Yeah, we will. Actually, the next section is in 14.5. Is it 14.5 or yeah. Yeah, 14.5, we are going to talk about gradient in 3 dimensions. The only thing that we are going to have is the gradient will be the partial derivative in the with respect to x is in the x direction, and the partial derivative with respect to y will be the y direction, and the partial derivative with respect to z is going to be in the z direction. Yes, and we need actually to learn gradient in space, because gradient vector, it is one of the example is the radiating vector, any heat transform and so on. That can take place in space, and we will work with that as well. Okay, let us finish only gradient in 2 dimension. With 2 variables. That means 2-dimensional, and that is actually what I'm heading to show you now. And then we will work with gradient with 3 functions. Did I answer your question?
Yes, thank you.
All right. So here is the example for the function of f of xy, which is defined by the square root of x squared plus y squared. I want you to graph the level curve containing the point 34 and the graph the gradient and graph the gradient del f of xy at this point, because I want to have a clear picture of how the gradient and the level curve are actually behaving. So please do that. Actually, I started scribbling sell out, but it's fine. By the way, this surface is what? It is the upper, because if it is simply z is equal to x squared plus y squared, this is a cone with 2 knobs. But because this is radical, therefore the upper half of a circular cone, and which is this. And then now I want to find it. Okay, and this is my actually coordinate axis, x-axis, y-axis, and z-axis. And when you draw the surface, it is a cone. And this cone looks like this one. And now what we are going to do is, well, what will be the trace that contains x3, y3? Well, as you know, because f of 34, which is square root of 3 squared plus 4 squared, that is equal to 9 plus 16 under radical, which is equal to 5. And that means actually we will have a plane parallel to the xy plane whose z value is equal to 5. So let us make this one 5. And then I'm going to draw that plane. And when you draw that plane, it will intersect with the cone and will give us this circle. And if you project this one on the XY plane.
Could you move the paper down a bit, please?
Okay. If you project it, then what happens? It will be a circle centered at the origin, having radius 5. That is what is really happening. And then what will be actually the gradient? The gradient is coming out this way. That means del of f of xy in the direction. Now, what will be the rate of change? Then we are going to find the tangent line over here. So the gradients are just coming pointing out like this. This is really the geometrical interpretation you guys are going to do. So after we have done, actually we will draw what it looks like. I will project it. So what is really happening? If the level curve through 4 is a circle of radius, actually, yeah, the level curve. Through the given point, that is 3, 4, is a circle. X squared plus y squared is equal to 25. That is what happened. So I want to find that gradient that I told you, the gradient of f. What is that? Well, because this is radical function, as you know, I don't have to explain a whole lot. This is x over square root of x squared plus y squared, the partial derivative with respect to x, and that is the I component. And the partial derivative with respect to y, by similar argument, it will be y over the function itself, x squared plus y squared, and the radical. That is j. Then now, what is the gradient of f at the point 3, 4? Well, x is 3, and this one is 5, and y is 4, and this will be 5. And that's it. And as you see, this vector is orthogonal to the level curve. I draw it just simply and I showed you, but actually we can verify it. This vector is orthogonal to the level curve x squared plus y squared is equal to 25. So in other words, if we draw the circle, okay, hopefully it will come out good circle. And this is the circle I have on the XY plane. And let me draw my coordinate axis. That way it will be easier for me. Okay, this is Y axis and this is X axis. And now, if you want actually the unit graph in the X direction, 3 over 5, 3 in the Y direction 4, and it will be like this. This vector is the del. All right. If that is the case, now what we are going to do is really about the vector we don't care about location. We care about what? Magnitude and the direction. So we are interested in finding the value at 3, 4. If this is 3 and this value is 4, let us assume, and this is the point. And what happened? The gradient vector, this vector, you translate it, it will come over here. This is del of f of 3, 4, which is 3 over 5i plus 4 over 5j. And the contour curve, this is actually x squared plus y squared equals 25. And what happened? The tangent is going to be orthogonal to del. And this is the tangent line on the contour. So this is really what we need to know. And at this point, let me write it 3, 4. Okay, is it clear, guys? So what we have done is we have this cone, and we are asked to find the level curve containing 3, 5. The level curve on the surface is going to be actually the plane which is parallel to the xy plane at the value of z equals that constant, and that constant be achieved by plugging 3, 4, and that is 5. So the plane z is equal to 7 intersect with the surface z is equal to square root of x squared plus y squared will give us this circle. And if you look at actually a different value, you are going to have a concentric circle of radius r centered at the origin 0, 0. And specifically for this is going to be the level curve. And in that, the gradient is really coming out, and we can really justify it. It is this way. And the tangent is always touching the path exactly at one point. So the gradient and the tangent vector are forming 90 degree, or they are orthogonal. All right. Then now let us talk about property of gradient. And those properties are actually very important, especially for this class. And I will come back to them on Monday when we talk about it in section 14.4. 14.4, you have really enough, so we can really move on and do your homework. But 14.5, that is what will happen. So first, I want you really remember the algebraic rule of gradient. If the gradient of two vectors f and g are both known, then it's possible to find the gradient of their sum, difference, constant multiple, product, and quotient as follows. The sum of the gradient equals the gradient of the sum of each gradient. And the difference also, you can really calculate independently and subtract. If you have a scalar, actually multiple of a gradient function, you take the gradient of the function and multiply by the scalar. The product rule is analogous to actually product rule for the differentiation, which is the gradient of the product of two vectors is going to be the first, two function is the first function multiplied by the gradient of the second plus the second function multiplied by the gradient of the first. The order you can change it because commutativity. Quotient rule. Then what you need to do is you have to take the gradient of the numerator multiplied by the denominator minus the gradient of the denominator multiplied by the numerator divided by gradient square. And actually there are examples on the note. You can really do that. I hope this helps. And please do your homework up to section 14.4 and submit them. And hopefully this helps. And I will see you on Monday. Okay, let me see actually chat. All right. Okay, guys. Good luck with the quiz on Friday evening, in the afternoon, or Saturday. You can do it either ways. Okay.
Sorry, real quick.
Yes.
Which chapters of homework do you want sent on Saturday?
On Saturday, you are going to send chapter 13 only. Chapter 14, we are not finishing. So you sent already chapter 12, and actually, as I put it on the announcement, chapter 13 only. Okay.
Okay. Thanks.
I'm talking about the lecture note homework. Okay. But the warm up, follow the calendar strictly. Okay.
Yes. Yes. Thanks.
All right. Thank you.